All right, good day, chemistry students. Today we're going to talk about phase changes or changes in state. Fancy animations here. All right, so by the end of today, you should be able to explain the process of melting, freezing, sublimation, and deposition in terms of kinetic molecular theory. Not as much these ones, sublimation and deposition, despite their bolding, but we will mention what those are. But definitely uh, melting and freezing and as well evaporation and condensation, and how kinetic molecular theory explains this process basically. So you're going to also use the terms exothermic, endothermic, and a characteristic property and a vapor. So we'll talk about those. All right, so you're going to see this for the rest of the unit, or at least part of it here, and you'll see it on your quizzes probably or your tests. You may have to fill in certain spots on it. So this is just a what do you want to call it? A flow chart or a um, concept map of changing between different states. So as we add heat on the left here, you can see we're going to go from a solid to a liquid to a gas. And you guys know this already, I'm sure, at this point. Um, as you remove heat, you'll move from a gas to a liquid to a solid. Now, the terms for these, going from a solid to a liquid, is called melting or fusion. Melting, I'm sure you knew. Fusion, it's not like fusion like fusing elements together, that kind of thing, but it is fusion as in, like think about you have a glass full of ice cubes and you leave it for a couple hours, and those ice cubes essentially fuse into one another. So that's what it means by fusion. Uh, Vaporization, the state to go to gas from a liquid to a gas, is we're moving to a vapor, so you can hopefully remember that. And then going from a gas down to a liquid. Uh, Condensation, so condensing or liquefaction, so turning into a liquid. And then freezing or solidification, that one relatively makes sense as well. Either, you're turning into a solid, it's freezing, same thing. Um, if you notice on this chart, you've got deposition and sublimation here. So we have there are certain things and certain situations where solids will go straight into a gas and skip the liquid phase entirely, or go straight from a gas to a solid and skip that liquid phase as well. So that's called sublimation, going from a solid to a gas, and deposition, going from a gas to a solid. So let's talk about melting first of all. So going from a solid to a liquid, S to L, right? Uh, Obviously, that means that the solid is heated up. Now, this part may be a little counterintuitive. If I ask you, okay, well, if something is going from a solid to a liquid, let's say an ice cube to liquid water, um, is this endothermic or exothermic? Well, it's actually endothermic. You may think, well, it's heating up, so it's exothermic, but no, it's absorbing heat. That water, that ice cube, uh, is requiring energy to be absorbed to turn into a liquid. So it's actually endothermic. So think about rather what's being absorbed rather than the external temperature in that situation where it's, you know, like outside going from winter to summer, it warms up. But keep in mind that energy is being put into that. So it's an endothermic process. So that solid is heated up. Energy is that energy, that heat that's going in, we're using that. Well, it's being used to reduce the intermolecular forces, those IMFs that are holding those solid uh, water molecules, the ice molecules, together. So those IMFs, those are there because, well, there's always IMFs, but because there's so little energy, that's why it is a solid. The IMFs are stronger than the energy that's there between the molecules, the intermolecular forces that are they're holding those molecules together, holding them really, really tightly. But as we give it more and more energy, it's able to break those IMFs or reduce them to the point where those molecules can then flow around each other and are no longer stuck to each other the way they are as a solid, and that's what becomes a liquid. So those particles are able to move more freely as we add that energy. So if I was looking for this on a test, I'd be looking for something like keywords of uh, by adding energy, uh, you know, when we add heat, it adds energy, which reduces IMFs, something like that. Okay. Um, by reducing those IMFs, it allows the particles to move more freely, something to that extent. Okay. So this is kind of a characteristic property for depending on what substance you're dealing with. They all have different melting points. So melting point for water is of course 0 degrees Celsius. Melting point for something like iron would be, ridiculously high. And I mean, I can look it up, but it'll probably be what, in the thousands of degrees Celsius. So, you know, um, each substance has a different melting point, which is their characteristic property. And it very much depends. And the reason why those are different is because of the different amounts of IMFs. So iron has much higher IMFs than water, which is why the melting point has to be so high, because you need so much more energy to break those IMFs and get to a liquid. All right, vaporization. So going from a liquid to a gas, you're going to have the same kind of thing going on here. Energy is absorbed, so it's endothermic again to go from a liquid to a gas. And it's further breaking those IMFs. So that energy is put in to that liquid and you get a gas out, right? Particle motion increases. So those water molecules, for example, as they move faster and faster, they're able to escape that liquid form and actually go up into the atmosphere because they have enough energy to move around. So the characteristic property in this case is, of course, the boiling point, which again is unique for each substance. Okay, there's two different types of vaporization, so you do need to know the difference between these and how they work, and we'll talk about that here. So evaporation and boiling. I'm sure you I'm sure you thought of evaporation less than you thought of boiling here. When you were thinking of vaporization, going from a liquid to gas, you're probably thinking about boiling a pot of water or something like that. Okay, so boiling. Liquid particles at the bottom of, like, let's say our heated pot give enough energy to overcome IMFs. So in this case, we have the vapor released down lower in the liquid, that in the container, right? And when you look at your pot of water boiling, if you look down there, you can see that those bubbles of gas are actually being formed at the bottom of the pot because that's where the energy is going in, right? So, the energy coming out of your stove heats the bottom of the pot, puts it into the water at the bottom. That's the hottest spot. And so the highest amount of energy. And so that turns into a gas right at that point. Those molecules are getting enough energy um, to expand, to move really, really fast to the point where that vapor is released at that point. It turns to that vapor state. And then those bubbles rise to the top of your pot and then like bubble and then break. And then you get the steam coming off. The comparison or the by uh I can't think right now. It's like midnight and so my brain isn't working. I've been working all night. Um by contrast, that's the wording I'm looking for. By contrast, evaporation uh, is liquid particles on the surface have just enough energy to overcome those IMFs. So evaporation, think about like outside and you got your, your puddles in the parking lot that over the course of the day on a nice sunny day or whatever, will evaporate, right? And that's because they're getting enough solar energy to overcome those IMFs. They don't need the same amount of energy that it requires to boil. It doesn't need to hit 100 degrees Celsius to get to that temperature where it can evaporate. All it needs is enough to just overcome the IMFs on the surface. And I'll show a picture here right away of why that's different. So that same thing though, you get vapor released in this same situation. Um, what it requires for both of these situations is a relatively high level of energy. Now, less so for evaporation than for boiling, but you still need to be in the higher section of this curve of energy distribution. It's only the molecules that have the highest energy that are going to turn into a vapor. Okay, so the reason it works for evaporation is because the particles that are on the surface of that liquid, well, I'm always talking about water in these situations just because it's the most common to us, right? But the liquid on the top here has the least IMFs to overcome. This top molecule, and this is obviously very zoomed in at this point, only has, to connect to these 4 molecules around it here. Whereas one that's further down, even one really close here, has all of them completely surrounding. It has 6 molecules right around it. Plus it's trapped, right? So this top molecule is able to escape as long as it's got a high enough energy. So you got solar energy coming down on it, warming it up, giving it some energy, and it has less IMFs to overcome, so it's able to escape at that point. And I think we've got a fancy animation here. So you'd see, ooh, that's so bad. I'm sorry, guys. But it is still only the highest energy of what's in this water. Keep in mind that this temperature curve would be very different than something that's boiling water. We're not hitting, this doesn't mean that it's 100 degrees Celsius up here. This is just the curve of the liquid that's in this container. So this could be, 50 degrees or 40 degrees Celsius at the top end. And um, and it's not even temperature necessarily. It's just energy. All of these particles have different amounts of energy. I'm gonna show you. I gotta show you guys this just to show you what I'm talking about here. Just a second. You'll see in this simulation, um, this is on PhET, which is uh, a bunch of you've probably seen these before. Boy, it's really slow. I don't know why my internet's so slow right now. Um, 0 results. What's going on here? Oh, there we go. Okay, so gas properties, this one right here. Okay, let's look at energy. So as I put in particles, heavy or light, I'm going to put in heavy, the blue ones here. Okay, what you'll see, I'll put a couple pumps in here. What you'll notice, if you look at those particles, some are moving really fast comparatively, and I'm going to heat it up a little bit. We'll get some moving a little bit faster here. Okay. So some are moving really fast and then they bump into something and they go really slow. So you kind of have to watch them, right? But those fastest particles have the most energy. And then there's some that are like this one down here that's barely moving and then bang, it gets bumped. Whoa. And keep in mind, all these collisions are elastic, right? We've talked about that uh, in the last one, meaning they don't lose, they don't lose any energy. They transfer it to other things, transfer it to other particles, but as you heat this up, and I can let some out, I believe. Hold on, so that they're moving around a little faster, more consistently. Hold on, get a few less particles. Heat them up again here. See the temperature on the top rising up. So even when I heat it way up, you get some that are moving really fast and still some that are moving really, really slowly. So that's that curve uh, in that slide here. You've got some that are moving very, very fast, some that are moving really, really slow, and the bulk of it's kind of in the middle here. Only the fastest will actually be able to, the ones with the most energy will actually be able to escape. That's what I'm getting to. All right, condensation. So now moving the opposite direction, moving from a gas to a liquid. Kinetic energy of these particles here decrease as it cools, right? I mean, it makes sense. You're taking away energy essentially. So the kinetic energy, that means the energy of motion, right? Of those particles is going to decrease as it cools. And did I completely close that? No, it's still there. So as we cool it down, you can see that the particles are slowing down. So they have less kinetic energy. They have less motion that they're able to do. Now I'm getting pretty close to absolute zero. These things are barely moving. Okay. So as these particles slow down, then IMFs start to take hold. And this demonstration doesn't show it. I don't think there's, I think I have to go to a different simulation. I believe there's one that does show that. I'm trying to remember which one it is. Oh yeah, states of matter. Did I do this one with you guys? I can't remember. Man, you'd think my internet is crap today. Well, whatever. We'll come back to it. So as those particles slow down, the IMFs take hold and it becomes a liquid. Not quite, it's not talking about reducing the energy enough to go to solid at this point, but just to a liquid. Energy is released. So in this case, now we're actually exothermic. So as that gives off energy to it has to give off energy, right? It has more energy in gas state than it has in liquid. So it's going to give off that energy as it moves to a liquid state. Okay, moving from freezing to, condensation to freezing or solidification. So in this case, we're going from a liquid to a solid. Same thing, particles continue to lose energy at this point. It's exothermic because it's giving off that energy. And particle motion decreases even further. And you start to get IMFs that hold stronger and hold it into a specific solid pattern, either crystalline, sorry, crystalline, goodness. Again, after midnight here. So crystalline or amorphous, and you've seen this picture already, right? And so often the difference between these is the speed at which it cools, but it also depends on what substance you're dealing with. So I did give the example of obsidian, which is volcanic glass, right? But other lava will cool to become crystal form. So like a crystalline form instead of an amorphous form like that. So honestly, the only reason that lava cools to become amorphous, such as obsidian, is because it cools really, really fast. So you only get obsidian when you have You don't get it when it's those like slow lava flows. You get it when it's like an explosive kind of volcanic reaction or volcanic eruption where it's blasting out bits of lava. And so those bits are cooling really fast, those small chunks of lava. Or, if they hit water, then they cool really, really fast as well. So at that point, it basically the structure doesn't have time to form crystals. So they just solidify in whatever format they're in at the time they cool down. All right, so sublimation and deposition. Um, Sublimation going from that solid to a gas. So an example of this, it doesn't happen a whole lot in the natural world, but one example, if you think about like in winter, if it hasn't snowed for a long time and the fields are covered in snow, you may notice that the snow starts to leave after a while. It starts to just, maybe there's a very little snow and all of a sudden it's like, okay, where did all that snow go? It didn't blow away and it's been below freezing for a long time. It can even be minus 20 or minus 10, but you'll get sublimation where the top layer of snow is turning straight into a gas, actually. And that's just mainly due to the sun's energy at that point. An example of deposition is kind of the opposite, hoarfrost. You get those humid nights. Maybe you had fog, but it's below freezing, and it's actually like a super cooled water, but it doesn't have anything to form on until it touches something like a leaf on a tree, or some grass or whatever. And when it touches that, it instantly forms a crystal. So it goes straight from a water vapor to a crystal at that point, and that's deposition. And if you want to think of how to remember this, the difference between these two, just think deposit. So you're depositing a gas onto something, onto like a solid. So like I think of like those hoarfrost crystals that are depositing onto like tree branches. Um, Sublimation, you just have to remember it's the opposite, I guess. I don't know. If you can think of something, I haven't thought of an analogy. Um, I know they I know they make T-shirts with sublimation. Um, the ones that have like logos and stuff on them, but that aren't screen printed. That's sublimation. And so I would imagine, I don't know, I haven't looked into the process, but I would guess that they take a solid and heat it up in a vacuum or something. That might be what it is, to turn it straight into a gas and put it into the t-shirt fabric. Because I'm pretty sure it is some sort of a gas that is put into the fabric and it changes the color of the threads at that point. I don't know. I'm curious. I want to look into that. If someone researches that and lets me know, that would be cool because I don't have a ton of time to look into this stuff. Okay, so know the difference between those. Know that sublimation is going from a solid to a gas and deposition is going from a gas to a solid. Okay, we'll just look at this again and put in a couple things here. Ooh, fancy flash. So as we add heat, this increases the particle motion. This is how it's applying to kinetic molecular theory, right? As we remove heat, it decreases that particle motion. You're removing that energy. And as we remove that heat, it decreases the kinetic energy. So increase kinetic energy. Kinetic means motion again, keep in mind. So particles are moving. It has more energy. It's able to escape. As you decrease that heat, decreases that energy, decreases the motion, and those particles then deposit, become, go from gas to liquid and liquid to solid at that point. Okay, so when we remove that heat, it's increasing IMFs. And when we remove that heat, add the heat, it's decreasing IMFs. Okay, so hopefully you can do all that stuff and you know these terms at this point. Yeah, and make sure hopefully you took the notes on that. I didn't mention it at the beginning, but I'm guessing you guys know to do that.